So we're going to look at the intermediate value theorem. And what the intermediate value theorem says is if we have some continuous function, so it has to be continuous in order for this to hold, and it's continuous on some interval, and in this case, we call it AB, and let M be any number that falls between the y value when x equals a, which is f of a, and the y value when x equals b, which is f of b, then we know that there must exist some number c such that c is between our x values a and b, and f of c is equal to m. Okay, I think that if I draw this picture, it will explain it a little better. So if we have some graph, it has to be continuous. And we have some x value a, we have some x value b. So our point here, f of a, and our point here, f of b. So we can see that that is continuous on AB. And so what this is saying is there has to be some value of x that falls in between A and C that would give us the y value, any y value that falls between my y values, in this case, f of b to f of a. So there has to be some y value in here. So let's maybe say this is our y value m. So there has to be some x value, and that x value in there has to fall between that a and b. So this would be our c. So this could be helpful, in particular, if we're looking for where our graph is crossing the x-axis. Right? Because if, pull that down. If we have some y value, we know our function is continuous. Oops. So let's say that this is some value a, and this here, some value b. If I look at my y value at a and my y value at b, I know that my f of a is negative. And my f of b is equal to a positive number. And so 0 is a number that falls between f of a and f of b. So by this theorem, there has to exist. So therefore, by the intermediate, let's call it IVT, by the intermediate value theorem, there exists. So I'm going to start writing some mathematics. There's a symbol for there exists, which is a backwards E, capital E. Some x equals c, such that c is contained in the interval between a and b. So I'm just going to put those in there just so we can use them again. Okay, it tells us that there exists one. It doesn't tell us if there's more than one. So it's possible, right, that this could have been, this graph that I just looked at, could have been coming back and forth in here a couple times. I would know that there exists at least one C that is in there. That would make that 0, right? The other thing that it doesn't tell me, what if this first example, this graph actually, maybe it went above, came back down and like this. This right here is just telling me I know that there's some X value that's going to get me a Y value in between here. It doesn't tell me that the range goes above or below those Y values in between those X values. So let's look at an example. And before we do that, let me just make sure there's no questions. So we're going to use the intermediate value theorem to prove that each equation, actually we're just looking at one equation has a solution. And then we're going to use a graphing calculator. We're going to use Desmos on the computer to solve the equation. Okay, so if we're going to try to solve or see that this has a solution, let's set this equal to 0 first of all. And so let's subtract 4 on both sides. So to find the solution, we have square root of x plus 1 plus x minus 4 equals 0. Let's think about our graph. So if we were looking at the graph y equals this, square root of x plus the square root of 1 plus x underneath the radical minus 4 equals 0. Not equals 0, sorry. We need to talk about the domain. I know that the square root of x, that's continuous everywhere on the domain. I know that the square root of 1 plus x is continuous everywhere on our domain. And if I graphed y equals -4, that's continuous everywhere on the domain. So we need to look at the domain of this. And so let's look at the domain of each piece. So if I was just to look at the domain of y equals square root of x, we can't have any negative number underneath our radical because that gives us back an imaginary number. So the domain are all real numbers we can plug in to get back a real number. And so in this case, I know that x has to be greater than or equal to 0. Or another way to write that is 0 to infinity with that bracket on the 0. I also want to look at the domain of y equals the square root of 1 plus x. And so if I was to look at that, again, what's underneath the radical has to be a positive number or 0, greater than or equal to 0. And so 1 plus x in this case has to be greater than or equal to 0. If I solve for x, this is telling me that x has to be greater than or equal to -1. So my domain just for that piece would be -1 to infinity. Both of these pieces is in this equation. And so the domain of this, it has to satisfy both of these. So we're looking at the intersection of both of these sets, what they share in common. And so the domain for our whole function y equals the square root of x plus the square root of 1 plus x, and then outside -4. Well, the domain of both functions, the intersection of both functions, what they share in common, and what they share in common are all the numbers where x equals 0 to infinity. So it's 0 to infinity. Okay, so we know it's continuous, and we just said it was continuous from all numbers from 0 to infinity. We want to see, is there any way that we can show that if we choose some x value, we get a negative number, and another x value, we get a positive number. If we can do that, then we can say by the intermediate value theorem, there has to be some root. There has to be a solution for that equation, at least one.
Mr. Officer, really quick, what about the -1 to infinity? How come that doesn't?
Yeah. Because this function itself has both pieces, we have to look at our domain for this function has to satisfy that when we plug it in, we get back a real number. And so we have to look at the intersection of both of those sets. So if we looked at that first domain, right, we saw that it was everything from 0 to infinity. If we looked at the other piece, that was from -1 to infinity. The thing is, any number between -1 and 0, if we chose it and plugged it in, so if I chose -0.5, when I plugged it in for x in this piece, for the first piece, that's not a real number. And so you have to look at your trouble spots, if you have a radical, for each, more than one radical for each piece, and then look at what they share in common. And so the x values they share in common would just be from 0 to infinity. And we couldn't use any of the numbers from -1 to 0, because that would make this piece be undefined over the real numbers.
Okay, that makes sense. Yeah, I didn't see that at first.
Yeah, great question. So we just got to start choosing some values, and maybe we can call this f of x just so we don't have to write it down as much. Well, we know 0 is in our domain. What happens? Let's see if we plug in 0 here. And so if we go in and we plug in 0, wherever we see an x, we get the square root of 0, which is 0, plus the square root of 1 plus 0. Well, that's 1 minus 4. So f of 0 is equal to -3. So I want to think of some number that would give me back a positive output. I notice here that I'm really summing things, and then I'm subtracting off 4. So as long as I choose some value that would give me, when I sum this, a number bigger than 4, then I know it's a positive number. And so how about, I don't know, let's say 9. So if I look at f of 9, when I plug it in here, I get the square root of 9, which I know is 3, plus the square root of 10 minus 4. Well, 3 minus 4, so that's -1 plus square root of 10. I know the square root of 10. Well, 10 is between the two perfect squares, 9 and 16. So I know the square root of 10 is between 3 and 4. And so if I take some number between 3 and 4 and subtract 1, I know that this is a positive number. This is greater than 0. So by the intermediate value theorem, we know we have at least one solution between 0 and 9. We could shrink down our interval and see if we can get closer and closer and closer. So I could choose a number maybe a little bit smaller. So what about if we chose x equals 8? And so if I looked at f of 8, well, that gives me the square root of 8, which let's just write as the square root of 8 because I can't simplify that, plus 1 plus 8 is 9 underneath that radical, which we know is 3, minus 4. So square root of 8, that's minus 1. Well, square root of 8 again, right? Square root of 8, it's between the perfect squares 4 and 9, so it has to be between 2 and 3. So 2 and 3, a number between 2 and 3 minus 1, again, is greater than 0. So we can keep on doing this, and it would be easier if I started throwing things into a calculator. Let me pull up a calculator for us. So I just told the class, you can see Desmos in front of us. We're going to let it do some work to see if we could even get a better accurate solution or estimate of our solution. We saw that so far that f of 0 was a negative number and f of 8 was a positive number. So by that intermediate value theorem, there has to be a number between 0 and 8 where the function crosses the x-axis. And we've said that at least once. So let's look at f of 1. Let's see if we can narrow this. So f of 1 is still a negative number. So now we've shrunk our interval from 1 to 8. Let's look at f of 2. F of 2 is still a negative number, so I've shrunk that even down further. F of 3, still a negative number. F of 4, positive. Okay, so right there, I know that when x equals 3, my output y value is negative, and when I plug in 4, my output y is positive. And so now I know that there's 1 0 or a 0, at least 1 0, between my x values 3 and 4. And so we can keep doing this by shrinking our interval down further and further. But it also asked us to actually use the graph to help us. And so we can now just say by the intermediate value theorem, we know that there's some solution between, there is some solution between x equals 3 and x equals 4. And so now I'm going to bring over Desmos and we're going to graph that function. So notice over here, we can see that it's crossing our x-axis between 3 and 4, which we said that it was. And in this program, you can just kind of highlight. And notice that we just found that exact solution. Y is 0. And when x is 3.516 or approximately, this could be rounding.